Move over to that one there. Fantastic. As Duncan said, I'm Thomas. I'm a PhD student here at the University of Manchester, working with Clive Dickinson and Stuart Harper on the COMAP Galactic Plane Survey. And so today, really, my talk's going to be roughly split into two sections. For the first half of it, I'm going to give you a rough overview of COMAP, so what the collaboration is, what our main science goals are, how we resolve the data down. And then in the second half, I'm going to summarize the main conclusions out of our first Galactic Plane Survey paper, which was released onto arXiv late last year and has just been accepted for publication in the Astrophysical Journal. So without further ado, let's start. What is the COMAP collaboration? Well, the COMAP collaboration is a collaboration of 37 members across 11 universities, with our main PI being Kieran Cleary over at Caltech, and then myself and my two supervisors down at Manchester in the bottom left-hand corner there. On the right-hand side, you can see a picture of the collaboration, although having said that, it has changed quite significantly and expanded since then. And COMAP itself being the CO Mapping Array Project. Next, sort of talking about the dish you saw in the background of that photo, the COMAP Pathfinder. It's a 26 to 34 gigahertz frequency instrument, so Ka band, with 1496 channels over that entire frequency range, so with a 2 megahertz spectral resolution. The instrument itself has a fairly consistent 4.5 arc-minute beam, full width half maxima across the full set of channels. And then one of the things that really makes COMAP stand out as an excellent instrument to conduct a survey with is that we have 19 forward-facing pixels in a lattice arrangement, which allows us to take 19 fairly independent realizations of the sky at any one point in time, meaning that we can go fairly quickly on it. One thing to note, though, is that unlike some of the other experiments, I believe, that are being represented with Cosmoglobe, we're an intensity-only experiment, so we don't actually produce any polarization information. We're purely Stokes' I. So I work mainly on the Galactic Plane Survey, which is the secondary goal of the CO Mapping Array project. The main goal being in linear intensity mapping with the CO10 line, redshifted from forming galaxies. So for our secondary science goal, what exactly are the science arguments to really push that? So the first one is to fill in a gap in frequency coverage. At the moment, there are only two main Ka band surveys available with relatively small resolutions. So we have the VSA GPS, which operated at 33 gigahertz and had 13 to 40 degree scales. One of the figures of which you can see in the bottom left-hand corner here, if you're able to see my mouse. And then the second being the Planck LFI 28 gigahertz map with a resolution of 32.3 arc-minutes, which was single dish. So we're retaining all of those larger scales. And so having COMAP there, and even filling in some of the larger scales in COMAP with Planck, we can really help plug that gap and provide high resolution data for the astronomical community. Second of all, galactic science. Such a map has a huge array of applications, from AME all the way up to studying diffuse emission around the galaxy. I've only listed 8 here, so AME surveys, flat spectrum supernova remnants and PWNE, infrared dark cloud emission, looking at an RRL survey, molecular lines, H2 region, star formation, diffuse emission, the list goes on. And of those, the ones that are highlighted in red, we've touched on briefly in the first paper, the Rennie et al. 2021 Early Science 6 paper. And then finally, looking at CMB applications, the COMAP Galactic Plane Survey can be used alongside the Planck LFI maps to fill in small scales, which will lead to a better understanding of emission mechanisms leading to AME, and then finally giving you potentially improved component separation and foreground subtraction when really digging down to studying the cosmic microwave background. So before we even get to maps, we first obviously have to take the TOD, the time-ordered data, and pull it through and process it. So the way that we do that is, first of all, taking the data from a server over at Caltech where the pathfinders sighted, syncing it over locally, and then calibrating it. And the way that we do that is we calibrate on a cal vane, which is a hot, cold load calibration, where we cover up the feeds with a metallic surface, which is assumed to be a black body at ambient temperature, and hot, cold calibrate on that. At this point, we have a level 2 file where we'll pull out statistics on 1/f noise, where we'll look at atmospheric slabs, etc. We'll also do some sigma clipping to try and pull out any spikes in the data. And then if we're looking at a calibration observation, we'll do the source fitting at that stage. Moving from a level 2 file to a level 3 file, we're looking at astro calibrating now. So using those calibrator observations, implementing the calibration from there, and getting a much more definitive calibration, which is good on the percent level. So that's ultimately most of the difference between a level 2 and a level 3 file, in addition to some of that clipping. Finally, from level 3 to having a final map, we then destripe after having cut the data on the derived statistics from level 2, which gives us our final set of maps. So a final set of 8 1 GHz wide maps covering between 26 and 34 GHz. Obviously, as part of this, we face several challenges, and one that's been noted by quite a lot of people is indeed the atmosphere. So COMAP actually sits between two telluric lines that are quite prominent. So the water line over at 22 GHz and the oxygen line up at 61 GHz. The figure on the left-hand side shows you TSIS contributions based on a very brief model. As your relative humidity changes at ground level, and you can see we're actually really sensitive to this. So really we want to cut down on the amount that we're adding to TSIS effectively, because that then gives us those 3 different effects. So we have a TSIS contribution, we have some sort of absorption of astronomical signal, and then finally you have the 1/f contamination driven by turbulence in the high atmosphere. In order to try and do this, as I said earlier, we do cut on derived statistics. So on the left-hand side here, you can see a series of binned histograms for spectral index on the top. And then what we're finding is one of our main statistics to cut on, which is what we call the root power at 0.1 Hertz. So what we do here is we take the power spectrum, so the 1/f noise fit, and we look at the amplitude of that at 10-second timescales, look at that distribution for all of the different observations and just put in a hard cut. And that's mainly the way that we cut the data for the Galactic Plane Survey. That's used alongside a series of observer flags. So in case there was maybe a small hardware fault, or whether there's something that someone has observed qualitatively in the data, we use those observer flags as well to really narrow down our data selection, which results in a season 1 observing efficiency of around 70 to 80%. We also have some lower level effects. So one of our main early challenges actually was peaks in TSIS measurement. Initially, we just put in a hard mask for this, but recently we're noticing that these start to move around as we've had small bits of maintenance happening to the telescope. And so at the moment, the way that we're dealing with these is to apply a strict conservative mask that's based on reviewing the level 2 data and reviewing our derived statistics. And so implementing those based on the time of each observation, which we're finding at the moment to be a very, very effective way of doing that, which ultimately over the entire frequency range keeps us about 80% of the channels, although those TSIS spikes aren't evenly distributed, so that can vary band to band. Once we've got our TOD processed, one of our main tools is destriping, which I note that a lot of other experiments are using as well. So assuming that sky model where our TOD is equal to some map component of the actual sky, plus some correlated noise component, plus some white noise component, and solving back for the map. Our current maps are using 1-second destriping timescales, which corresponds to around 18-minute scales on the sky, taking into account our slew speed. And that suppresses noise by factors of 4 on scales up to 30 arc minutes, and then beyond 30 arc minutes, even greater than that. And at the end of the day, that gives us a noise in our maps of roughly 4.6 plus or minus 1.2 millikelvin arc minute squared. And again, that can change patch to patch depending on coverage. To show you what a real difference this means, I've just put together a quick figure here. So on the left-hand side, you can see a naive binned map of one data selection. On the right-hand side, you can see the destriped map. And in the middle, we've got the difference between the two. There are mainly two take-homes from this, in the fact that, first of all, it is really helping us to suppress those that large-scale noise that comes with 1/f. But finally, also that it does emphasize that we still need to keep those cuts very harsh and keep them conservative, because you can still see one artifact in this image, which again emphasizes the need for good data cuts and a good understanding of the data, which, as ever, we're permanently working towards and striving for better on. Once we've got that far, we end up with finished maps. But just as a quick side note, one thing that we're currently working on is to do a good deconvolution with the Pathfinder beam. So we already have very accurate beam models, such as the one on the left-hand side here, which is taken from the early results 2 paper, so the instrument paper, so Lam et al. 2021. So the left-hand side here, this is a map of the modelled far outside lobes, so a map of the modelled beam. On the right-hand side, based on calibration scans of Jupiter, which appears to us a point source, we have a series of beam maps derived. And then in between, you can see a comparison of measurement against our models. And we find that there's generally a very good agreement. And so based on these beam models, we're currently working to implement beam deconvolution, which should give us sub 3% accuracy for the full survey. But again, just to make you aware, this is ongoing work. For the bit you've all been waiting for, this here is our first published set of maps. So the COMAP Galactic Plane Survey between 20 and 40 degrees galactic longitude, covering galactic latitudes with magnitudes less than 2 degrees. And so here in this labeled map, we have the Parkes 5 gigahertz contours in white over the top of the map up here. All of the orange boxes denote Westerhout regions, which generally we find a very good way of sort of starting to get to know your way around the galactic plane and navigating your way around. And then all the pink boxes are the supernova remnants that we find that we're able to detect at 30 gigahertz, excluding, of course, W44. Now, the main focus of our first paper was W43, so Westerhout 43 in the middle. Main reason for that being that it's this mini starburst region. Estimates of star formation rates go anywhere from 0.01 to 0.1 solar masses per year, depending on the measure that you use. But ultimately that it's this very bright region in the radio sky that we thought was a good start to be able to ensure that the COMAP Galactic Plane Survey would be able to get down to the signal to noise required to be able to resolve some of the higher latitude sources further away from the center, the galactic center. Looking immediately at starting to compare these with other surveys, this is figure 3 from the first look paper. So on the left-hand side here, you can see a TT plot of the 30.5 gigahertz COMAP band against Planck 353. And on the then on the right-hand side, you can see a comparison against the Parkes 5 gigahertz survey, along with their associated Pearson correlation coefficients in the top right-hand corner, where we see a much tighter correlation with the lower frequencies. And then further going on the correlation with the 5 gigahertz map, we can estimate that an AME fraction of roughly 22% based on this very basic analysis, which of course we can back up with SEDs as we do later on. Just giving you a pair of example SEDs here, so spectral energy distributions for 2 sources that we found particularly interesting within the survey that are shown in this map on the top right here. So the only difference really between these 2 sources, as far as we could make out by eye, was that one of them is part of this diffuse structure, this diffuse C shape, whereas the other one is out on its own. And if you look at the 2 SEDs here, with the individual data points shown as the black dots, non-filled in dots denote that they weren't used for the actual fitting. And then the individual components given as, so a dashed line for free, a dotted line for thermal dust, and then dash for an AME curve. We can see that that source 2 has an AME bump, whereas source 1 doesn't, which would infer in this region that potentially it may be diffuse AME we're looking at. And so that's just one story for 2 SEDs. But in the paper overall, we present 9. And looking overall, we see a generally good agreement between the fitted flux spectral index within the COMAP bands themselves, and then the flux index for the actual model. And so we're showing really that the 8 COMAP 1 gigahertz bands that we derive maps for, potentially that spectral index does actually carry quite a bit of value and quite a bit of influence on these fits. But it's also notable that most of these AME models show a rising spectrum within the COMAP bands. Unfortunately, this is down to a lack of high resolution data between 40 and around 200 gigahertz to be able to constrain these models any further, which hopefully will become available in the near future, so we can pin these down a little bit more. But ultimately, what these result in are peak frequencies of these AME models that roughly average around 40 gigahertz. So very high peak frequencies. Looking at the dust temperatures as well, which of course may indeed be influenced by that. We find dust temperatures of roughly 23.5 degrees across those H2 regions, just taking a very crude average, which is notably higher than Planck. However, obviously the galactic plane is likely to be much warmer than the rest of the sky, where most of the Planck averaging comes from. Moving on from H2 regions, we also find some supernova remnants. So at 30 gigahertz, we can only see things with a very, very flat spectrum. So the 6 here we find with indeed very flat spectra. Of the 6 here, if you attract your eye down to W44 in the lower left corner, this was a particularly interesting one for us when we initially found it, because the in-band COMAP spectrum agreed almost perfectly with most of the other literature flux values, apart from one given by the team at the Sardinia Radio Telescope just a couple of years ago, who show a spectral turn-off somewhere between 10 and 12 gigahertz. Sorry, between 10 and 20 gigahertz. And so we're potentially showing that this is a much flatter spectral index, and that there is actually no spectral turnoff. But overall, for all of our supernova remnant SEDs, we find that either our values agree with current literature values, or that we're showing spectral turnoffs, which is, I suppose, as one would expect. Finally, something that we didn't initially think was quite going to turn out as well as it did last time I spoke to on one of these Cosmoglobe talks, was in the sense of RRLs. So we found out within the last year that actually we are able to spectrally resolve hydrogen radio recombination lines within our data, specifically the 58 alpha to 62 alpha radio recombination lines. Due to COMAP's 2 megahertz spectral resolution, we're not able to derive an awful lot of velocity information from that, as we're only sensitive to 20 kilometer per second resolution. However, that's still enough to be able to do an integrated hydrogen RRL map, as you can see a sample of in the top right-hand corner here. Now, obviously, this has quite a lot of value in the fact that it'll have similar systematics to the main COMAP continuum survey and could be used as a free template. And hopefully, once the survey is concluded, we'll be able to release this alongside the main continuum survey for use by the astronomical community. And we're hoping to effectively implement this on the entire galactic plane. So hopefully this will really feature an awful lot more in coming papers and certainly in coming work. And then sort of looking forward and looking towards the future of the COMAP Galactic Plane Survey, this is the picture I showed you about a year ago, back in June 2021, where we'd only covered between 20 and 40 degrees galactic longitude. About a year later, we've covered an awful lot more than that. So we've almost tripled our coverage, covering between 20 and 60 degrees galactic longitude, and then now beginning on a further patch between 110 and 130 degrees galactic longitude, which we're currently working on. Fortunately, there is a small break just due to weather, but that is being recovered as a priority within the next observing sessions. And so hopefully you can see how this is going to develop and hopefully be of use to Cosmoglobe and implementation of the Commander pipeline moving forward. And then just overviewing everything that I've said, COMAP is a 30 gigahertz, 5 arc-minute survey of the galactic plane visible from the Northern Hemisphere. We've currently released maps in our paper between 20 and 40 degrees. However, we do now have data covering up to 60 degrees with an extra patch between 110 and 140. The first results are released in Rennie et al. 2021 as part of the COMAP Early Science Series. In terms of data availability, we are planning to release all of our maps after the survey concludes in 2022, 2023 time. We've currently not got any plans to release the time-ordered data, but potentially we can release this upon request. However, the data volumes would be on the order of terabytes. Just, I suppose, an advanced warning there. So in that case, thank you very much for listening. A quick slide showing our thanks to our various funders. If anybody has any questions, please feel free to ask.